Hello viewers, the word equation must be a very familiar one to all of you. You must have come across linear, quadratic and of course trigonometric equations. Today we are going to discuss differential equations. Now what a differential equation is? Well, the definition says differential equation is an equation containing an independent variable and differential coefficients of dependent variable with respect to independent variables, or more specifically it can contain differentials dx or dy. Once that definition is given to you, can you form examples of differential equations? Well, write any expression involving dy by dx or dx by dy, and that will give rise to a differential equation. Take a look here. We have examples which says dy by dx is equal to x square y, a differential equation, or more elaborately y is equal to x dy by dx plus under root of 1 plus dy by dx whole square. You can have second order derivatives involved, can give rise to something like d2y by dx2 equal to sin x. When differentials are involved, as we are going to bring them in many cases, it will look like x square plus y square dx minus 2xy dy equal to 0. These are just some of the examples of differential equations. Just as polynomial equations are classified in terms of the degree into linear, quadratic, cubic, etc., we have classification for differential equations based on what we call as the order and degree of the equation. So what will be the order of a differential equation? The definition says order of a differential equation is the order of the highest order derivative appearing in the equation. When you have the highest order derivative, it's easy to locate. Take a look at these examples and see if you can decide on what will be the order of this equation. Obviously, the order can be easily identified because you have the second order derivative appearing as 2. In the next one, you have d3y by dx cube and this one is dy by dx. So, the order of this differential equation will be 3. Here dy by dx is appearing, no problem, even if it is in the denominator. For order, it is very clearly identified to be as 1. The second concept, that is the second way the classification is done, is a more careful one to be observed and learned, and that is what we call as the degree of a differential equation. So, what is the degree of an equation? Take a look. Degree of a differential equation is the degree of the highest order derivatives. Note this point, when differential coefficients are made free from radicals and fractions. That's again an important point to be kept in mind, so that if at all the equation involves fractions and radicals, they have to be first removed. So, the degree is the power in a sense of the highest order derivative involved in the equation. Again, if we go back to the examples we just saw, you will be able to see how to decide on the degree. For the first case, highest order is d2y and power of that is 1. So, the degree of the differential equation will be 1. Second example, don't be tempted with this 4 being more than 2. What we have to look at is the power of the highest order derivative. In this case, it happens to be 2. So, the degree of the equation will be 2. For the last one, you have to see that the derivative or dy by dx, if it at all appears in fractions, have to be first put in the straight form. And to do that, you can always bring it in the numerator and it will become dy by dx whole square. So, the degree is not 1 as it appears, but it is equal to 2. If radicals are involved, more work is involved. Take a look at this example. We have 1 plus dy by dx whole square to the power 3 by 2 equal to k d2y by dx2. If you have to identify the order, then order will be right 2. But the degree is not 1. Degree as it is cannot be identified. First we have to adjust this power here. So, we can remove the radical, that is we can remove the square root by taking square of both the sides, and the equation will change into 1 plus dy by dx whole square to the power 3 is equal to k d2y by dx2 whole square, taking square of both sides. And therefore, the degree of this equation can be identified as 2. So, this is what you have to keep in mind before identifying what the degree is. Another classification is termed in terms of the linear or non-linear differential equations. So, let us see what linear differential equation is. The definition says that linear differential equation is an equation in which the dependent variable and its differential coefficients occur only in the first degree and are not multiplied together. Not multiplied together means if you are talking about the function or equation being linear in y, then y and dy or dy by dx should not be multiplied together. The variable y should not occur in the powers more than 1. So, you should not have any terms like y square or sin y appearing in the equation. Let us see if you can identify which of the given equations are linear or non-linear. The first one, very clearly there are no y square terms throughout, y and dy by dx are not multiplied anywhere. So, the first one is clearly a linear equation. Second one also is a linear equation. It is not that if you have second order derivative, then the equation does not come in the category of being linear. It should not have a power. So, you can have second order, but it will always be the first degree, which will have the characteristic of being termed or identified as linear. And so, the second equation also is a linear equation. The third case, can you identify? Y into dy by dx is a clear signal that this is a non-linear equation. And so, we have to keep these characteristics in mind while solving and while learning the methods of solutions of various differential equations. But before that, once you know what differential equations are, if you have to form differential equations, what will you do? Well, one thing that you have to keep in mind is the use of the term arbitrary constants. Now, if you have an equation y is equal to mx represents family of straight lines passing through the origin. For various values of m, you get various members of that family. And so that m is what we refer to as arbitrary constant. Now, if we want to get a differential equation which represents this family of curves, then we have to remove this arbitrary constant. And to do that, what we do is follow a simple technique. Differentiate your function the number of times as the number of arbitrary constant available are present in the equation, and then eliminate those constants. In this one, it is a very simple task. You have m, only one arbitrary constant, so differentiate it and you will have dy by dx is equal to m. Removing this m is the task. Eliminate means put it back here, and you will have a differential equation which represents the family of curves or family of lines passing through the origin as this. But of course, the task is not always so easy. Let us take a question where two arbitrary constants are involved. The question says form the differential equation corresponding to y square equal to m times a square minus x square by eliminating m and a. To do that, what you have to do is start with first the understanding that there are two arbitrary constants involved, so you have to differentiate twice. Taking the first derivative, you have 2y dy by dx is equal to minus 2mx. And then what I am going to do is, for convenience sake, rewrite this not only by cancelling that 2, but also bringing in the notation of the first derivative written as y dash as equal to minus mx. And then if you do want, you can always go back to dy by dx, but it will save time to write it as y dash or y double dash. You can also use y1, y2. Differentiating it again, you will have y dash square by the product rule plus y double dash is equal to minus m. These are the two equations which we have to use to eliminate the arbitrary constants, and that can be done directly. You can put the value of minus m from 2 in 1 and you will have your equation turning up as y dash is equal to y dash square plus y double dash into x. It can be again rewritten as x y dash square plus x y double dash minus y dash is equal to 0. Right? To give it more particularly the form of a differential equation, you can always rewrite it as this. Rewriting y dash as dy by dx, y double dash as d2y, you will have the differential equation representing the given function as what we have here. Now the question on formation of differential equation can be asked in a slightly different form also. Instead of giving you the function, the question can say, take a look, find the differential equation of all the circles which pass through the origin and whose center lies on y-axis. So the first thing here is to get the equation which represents such family of circles. And what family are we talking about? Circles whose center lie on y-axis. So you can take the center to be 0, a. It passes through the origin. So what will be the radius of the circle? Right, a. And therefore the equation can be written as x minus 0 whole square plus y minus a whole square equal to a square. And that simplifies into x square plus y square minus 2ay equal to 0. And so we have the equation for which we have to form the corresponding differential equation. Now to do that, again you have only one arbitrary constant, so we will differentiate x square plus y square minus 2ay equal to 0. Differentiating it, you will have 2x plus 2y dash minus 2a y dash equal to 0. This is same as writing x plus y dash minus a y dash equal to 0. From here a comes out to be x plus y dash by y dash. We have to aim at eliminating a. So to eliminate a, we have got the value of a, and then we can substitute it back in the equation x square plus y square minus 2ay, and that gives rise to the equation, differential equation, as x square plus y square minus 2 times x plus y dash by y dash times y equal to 0. You can further simplify it down and write it as x square plus y square minus 2x by y dash to y minus 2y square equal to 0. It can be further simplified as x square minus y square minus 2xy dx by dy equal to 0. And this is what we have as the differential equation representing family of circles whose center lies on y-axis and the circle passes through origin. Now we come to our main objective, and that is to find the solution of a differential equation. The word solution I think is clear to everybody. We have to find that value of the variable or unknown which satisfies the equation. Here we have differential equations, so we can think of the solution as that function or the y expression which is going to satisfy the differential equation. So for that we have to remove the differentials and bring in the function y and x independent of the differentials. So the inverse process of differentiation, that is integration, is going to be used. Let us consider an example. Question says find the general solution of e to the power x plus e to the power minus x dy by dx equal to e to the power x minus e to the power minus x. What we can do is write dy by dx to be equal to e to the power x minus e to the power minus x and bring this term to the denominator. The integral of dy by dx with respect to x is simply y. So that is exactly what we will do. We will integrate both the sides with respect to x, and we have integral dy by dx with respect to x equal to integral of e to the power x minus e to the power minus x by e to the power x plus e to the power minus x with respect to x. Now this is also no trouble. What we end up with is y equal to log of e to the power x plus e to the power minus x and the constant of integration. The constant of integration is written only on one side, because if you have a constant here, it can be combined with a constant on the other side and then again reduces to one constant. Another point that I would like to bring out is we set the question as find the general solution. The word general is only there because this C can take infinite values, and so what you have got is not one solution but again a set of relations, a family of curves which satisfies the given differential equation. Now the method of finding the solution will not always be so simple. It depends on the equation that you have as to what and which method has to be used. We will start with our first category, and that is of what we call as variable separable. So we have a method known as variable separable method, and as the name suggests, what you have to do here is separate the variables x with dx, the differential x on one side, and the terms which have y with differential y on the other side. Take a look at this question. We have find the general solution of 3e to the power x tan y dx plus 1 minus e to the power x sec square y dy. What you have to aim for is, as I said, an attempt to write your expression or equation in the form fx dx equal to gy dy, all terms of y on one side and terms of x on the other side. That can be achieved quite easily here if you rearrange the terms, and that is where your observation is going to be of use. Dividing by 1 minus e to the power x dx, and on the other side if I take sec square y dy, it will be negative sec square y dy divided by bringing the tan y to the other side as this. This negative can be easily absorbed on the left hand side, and that is exactly what I am going to do. So it can be written as e to the power x minus 1 in the denominator dx equal to sec square y by tan y dy. And now we are ready to solve our equation by integrating the left hand side with respect to x, the right hand side with respect to y. And that will give you integral 3e to the power x by e to the power x minus 1 with respect to x equal to integral sec square y by tan y dy. Both the sides are very easily integrable. Here, what will be the result? 3 times log e to the power x minus 1. You can see for yourself, if you put e to the power x minus 1 as t, then ex dx is there in the numerator, expression comes out to be this. You can skip that elaborate explanation of the substitution method and write it directly by the observation. Same here, tan y equal to t, sec square y dy is there. So, this also simplifies to log of tan y and constant of integration comes on one side. Now, in some of the questions, it is quite possible to absorb this constant of integration and the log that is appearing throughout and remove the log ultimately. So, what we can do here is, since this is only a constant, it can always be written as log of certain constant number. So, I can write it as plus log of, say, the constant k. These two terms using the properties of log can be combined into k times tan y. On the other side, this 3 can be absorbed here as log of e to the power x minus 1 whole cube. So, I can equate the terms and we will have e to the power x minus 1 whole cube is equal to k times tan y. And this can be taken as your final solution for the given differential equation. The technique remains the same. What you have to learn is observe and decide whether it is possible for you to separate the variables. Consider another problem. Solve y minus x dy by dx is equal to a times y square plus dy by dx. Again, if we are able to collect the terms on one side along the y and of x on the other side, it's termed as a question which can be solved as by the variable separable method. That's what I have been able to do. Bring ay square here, you have a plus x dy by dx. So, the differential has to go up, and so rearranging the terms, can I write it as dx by a plus x equal to dy by y minus ay square, which can be written as y into 1 minus ay, and that is what we have to get. And now the process is simple. Integrate left hand side with respect to x, right hand side with respect to y. You can have it alternated. You can have x on the other side and y on the left hand side. Integrating, you will have simple integration again. Log of a plus x is equal to, check if you get, log of y minus log of 1 minus ay plus the constant of integration c. And again, as in the previous one, I can adjust everything all together as log of y into a constant k by 1 minus ay. You can even write the c directly as log of c, and therefore I can have my final solution as ky by 1 minus ay. You want to adjust it further, you can write it as yk is equal to a plus x into 1 minus ay, and that will be the solution of the given differential equation. Now, there are questions and forms where the question does not directly come under the category of variable separable. That is, you are not able to separate the variables as the equation is, but using method of substitution, we are able to do though. So, which questions or which forms are we able to do that? Consider 3 examples that we have here, and you will be able to identify the form or the category that they belong to. Take a good look, and now if I say that they all come in the category where dy by dx is the function of ax plus by plus c. That is, dy by dx is a function of the linear combination of x and y. So, I can't separate x and y, but if I take a special substitution, and the special substitution is to take ax plus by plus c to be equal to t, then the equation will work out. Let us see if it does. Consider dy by dx equal to x minus y plus 3 by 2x minus 2y plus 5. Very much a form as we discussed right now, and so here you can put x minus y as t or even x minus y plus 3 as t, and therefore before going further, remove your dy by dx. You have to replace that. So, differentiating, you can have dy by dx turning out to be 1 minus dt by dx. So, your equation will be 1 minus dt by dx is equal to x minus y is t. So, it is t plus 3 by 2x minus 2y will become 2t plus 5. And now try to separate the variables. To do that, dt by dx can be written as 1 minus t plus 3 by 2t plus 5. This is same as rearranging and taking the LCM, 2t plus 5 in the LCM, and you are left with only t plus 2. There is no x here, so very conveniently we can write it as 2t plus 5 by t plus 2 dt equal to dx, and thus we have achieved that variable separation. Integration comes next, integrating left hand side with respect to t and right hand side with respect to x. To integrate the left hand side, what? We have to always learn and keep in mind, if the numerator's degree is same that of the denominator, then first divide. When you divide, you should get 2 plus 1 by t plus 2. Are we getting that? Right. So, this is what you have as the left hand side, and the right hand side is completely and directly written as x plus c. We are nearing the result now. This is 2t plus log of t plus 2 equal to x plus c. And do not forget to replace t by x minus y as we had started with that substitution. And this is what you will have ultimately. A minor adjustment is possible, so we can always do that and write it as x minus 2y plus log of x minus y plus 2 equal to c. And that is what you have as the solution of the given differential equation. We will continue with more on the methods of solving differential equations in our next program. Thank you.